The existing branch circuit protection is properly rated for the motor but may not be adequate for the ASD. The National Electrical Code, or NEC, requires branch circuit protection to be sized based on the motor full load amps, or FLA. The FLA of the motor is typically indicated on its nameplate. The NEC allows for the use of fuses or circuit breakers to provide branch circuit protection. The fuse size should be 175% of the motor FLA, and the circuit breaker should be 115% of the motor FLA. The wire size should be 125% of the motor FLA. The disconnect switch should be rated for 115% of the motor FLA. Since the ASD is rated for a higher horsepower, it may draw more current than the motor. The NEC does not provide specific guidance on sizing branch circuit protection for ASD. However, it is generally recommended to use branch circuit protection that is sized for the maximum current that the ASD can draw. The ASD manufacturer should be consulted to determine the maximum current that the ASD can draw. Once the maximum current is known, the branch circuit protection can be sized accordingly. It is important to note that the branch circuit protection must be sized for the maximum current that the ASD can draw, even if the motor is not operating at its full load. This is because the ASD can draw current even when the motor is not running. In summary, the existing branch circuit protection is properly rated for the motor, but may not be adequate for the ASD. The ASD manufacturer should be consulted to determine the maximum current that the ASD can draw, and the branch circuit protection should be sized accordingly. To further elaborate on the selection of appropriate branch circuit protection for motors and adjustable speed drives, it's essential to delve into the specific requirements and considerations outlined in the National Electrical Code, or NEC, as well as best practices for ensuring both safety and optimal performance. The NEC provides comprehensive guidelines for electrical installations, including the protection of motor circuits. The fundamental principle is to safeguard the circuit components, such as conductors, motors, and associated equipment, against overcurrent conditions which can arise from short circuits, ground faults, or excessive load demands. Article 430 of the NEC is dedicated to motors and motor circuits, offering detailed instructions on conductor sizing, overcurrent protection, and control circuit requirements. When sizing branch circuit protection for a motor, the NEC mandates that the conductors supplying the motor must have an ampacity of not less than 125% of the motor's full load current, or FLC, as indicated in the motor's nameplate. This 125% factor accounts for the continuous nature of motor loads and provides a safety margin to prevent overheating of the conductors. The overcurrent protection device, which can be either a fuse or a circuit breaker, must be capable of protecting the conductors against overcurrents. The NEC specifies maximum allowable overcurrent protection device ratings based on the motor's FLC. For fuses, the maximum allowable rating is typically 175% of the motor FLC. For inverse time circuit breakers, the maximum allowable rating is typically 250% of the motor FLC. These percentages are higher than the conductor ampacity requirement to allow for the motor's inrush current during starting, which can be several times higher than the FLC. However, it's important to note that these are maximum values, and the actual overcurrent protection device rating should be selected based on the specific characteristics of the motor and the application. In cases where the specified percentages do not correspond to standard fuse or circuit breaker sizes, the next higher standard size is permitted. In addition to the branch circuit overcurrent protection, the NEC also requires that motors be provided with overload protection. Overload protection is intended to protect the motor itself from overheating due to prolonged overloads, which can damage the motor windings. Overload protection devices are typically thermal overload relays or electronic overload relays that are installed in the motor starter. These devices sense the motor current and trip the starter if the current exceeds a predetermined value for a specified time. The overload protection device rating is typically selected to be close to the motor's FLC, providing sensitive protection against overloads. When an ASD is introduced into the motor circuit, the sizing of branch circuit protection becomes more complex. ASDs, also known as variable frequency drives, or VFDs, control the speed and torque of the motor by varying the frequency and voltage of the power supplied to the motor. ASD can offer significant energy savings and improve process control, but they also introduce harmonic currents into the electrical system. Harmonic currents are non-sinusoidal currents that can cause overheating of conductors, transformers, and other electrical equipment. The NEC does not provide specific guidelines for sizing branch circuit protection for ASD, but it does require that the electrical system be designed to accommodate the harmonic currents produced by the ASD. This typically involves oversizing conductors and transformers, as well as using harmonic filters to reduce the harmonic current levels. When sizing branch circuit protection for an ASD, it's important to consider the maximum current that the ASD can draw, as well as the harmonic content of the current. The ASD manufacturer typically provides information on the maximum current and harmonic distortion levels produced by the ASD. This information can be used to select appropriate conductors and overcurrent protection devices. In general, it's recommended to size the branch circuit conductors for at least 125% of the ASD rated input current. The overcurrent protection device should be sized to protect the conductors against overcurrents, but it should also be able to withstand the ASD inrush current during starting. Some ASD manufacturers recommend using specific types of fuses or circuit breakers that are designed to handle the high inrush currents associated with ASD. In addition to the branch circuit protection, ASD also require input reactors or jerks to limit the harmonic currents injected into the electrical system. Input reactors are inductors that are installed in series with the ASD input power supply. They help to reduce the harmonic current levels and improve the power factor of the system. The size of the input reactor is typically specified by the ASD manufacturer. Furthermore, it is also crucial to consider the motor's service factor when determining the appropriate branch circuit protection and conductor sizing. The service factor is a multiplier that indicates the motor's ability to handle temporary overloads. For example, a motor with a service factor of 1.15 can safely handle a 15% overload for a limited time. If the motor is expected to operate continuously at or near its service factor rating, the conductors and overcurrent protection devices should be sized accordingly. In such cases, it may be necessary to increase the conductor ampacity and overcurrent protection device rating to account for the increased current draw. Consulting with the ASD manufacturer and a qualified electrical engineer is highly recommended to ensure that the branch circuit protection is properly sized and coordinated for the specific application. They can provide guidance on selecting appropriate conductors, overcurrent protection devices, input reactors, and other components to ensure the safe and reliable operation of the motor and ASD system. In summary, sizing branch circuit protection for motors and ASD requires careful consideration of the NEC requirements, the motor's characteristics, the ASD capabilities, and the application-specific demands. By following these guidelines and consulting with experts, it's possible to ensure that the electrical system is adequately protected against overcurrents and that the motor and ASD operate safely and efficiently. Always prioritize safety and adhere to all applicable electrical codes and regulations. Consider the ambient temperature and altitude where the equipment is installed. High ambient temperatures can reduce the ampacity of conductors, and high altitudes can affect the motor's performance. Make adjustments to the conductor size and overcurrent protection device rating as necessary to compensate for these factors. Verify that the overcurrent protection devices are properly coordinated with other protective devices in the electrical system. Coordination ensures that the protective devices operate selectively, minimizing the extent of any fault and preventing unnecessary outages. Conduct a thorough arc flash hazard analysis to determine the potential arc flash incident energy levels of the equipment. Use this information to select appropriate personal protective equipment, or PPE, for personnel working on or near the equipment. Install surge protection devices, or SPDs, to protect the motor and ASD from voltage surges caused by lightning or switching transients. SPD can help to prevent damage to sensitive electronic components and extend the lifespan of the equipment. Implement a regular maintenance program to inspect and test the electrical equipment. This includes checking for loose connections, damaged insulation, and other signs of wear and tear. Address any issues promptly to prevent equipment failures and ensure continued safe operation. Keep accurate records of all electrical equipment, including nameplate data, wiring diagrams, and maintenance records. This information can be valuable for troubleshooting problems and making informed decisions about future upgrades or replacements. Provide adequate ventilation for the motor and ASD to prevent overheating. Overheating can reduce the lifespan of the equipment and increase the risk of failure. Ensure that the ventilation openings are not obstructed and that the cooling fans are functioning properly. Use appropriate wiring methods for the environment in which the equipment is installed. For example, use liquid-tight conduit for wet or damp locations and flexible metal conduit for areas where vibration is present. Ground all electrical equipment properly to provide a low impedance path for fault currents. Proper grounding helps to protect personnel from electric shock and reduces the risk of fire. Label all electrical equipment clearly and accurately. This includes labeling circuit breakers, disconnect switches, and other components. Clear labeling helps to prevent confusion and ensures that personnel can quickly identify and operate the equipment safely. Provide training to personnel who work on your electrical equipment. Training should cover topics such as electrical safety, lockout tagout procedures, and proper use of PPE. Ensure that personnel are qualified and competent to perform their assigned tasks. Follow all applicable safety regulations and procedures when working on electrical equipment. This includes wearing appropriate PPE, using insulated tools, and energizing equipment before working on it. Stay up to date on the latest electrical codes and standards. The electrical codes and standards are constantly evolving, so it's important to stay informed about the latest changes. This will help to ensure that your electrical installations are safe and compliant. Conduct periodic electrical safety audits to identify potential hazards and ensure that the electrical system is in compliance with applicable codes and standards. Address any deficiencies promptly to prevent accidents and injuries. Implement a comprehensive electrical safety program that includes written procedures training and regular audits. A comprehensive electrical safety program helps to create a culture of safety and ensures that all personnel are aware of the risks associated with electrical work. Use only approved electrical equipment and materials. Approved equipment and materials have been tested and certified to meet applicable safety standards. Using approved equipment and materials helps to ensure that the electrical system is safe and reliable. Avoid overloading electrical circuits. Overloading circuits can cause overheating, damage to equipment, and even fires. Be sure to distribute electrical loads evenly across all circuits. Use ground fault circuit interrupters or GFCIs in wet or damp locations. GFCIs protect personnel from electric shock by interrupting the circuit where ground fault is detected. Install arc fault circuit interrupters or SIs in residential circuits. SIs protect against fires caused by arc faults, which are dangerous electrical conditions that can occur when wires become damaged or loose. Inspect electrical cords and plugs regularly for damage. Replace damaged cords and plugs immediately to prevent electric shock and fires. Use extension cords safely. Do not overload extension cords or run them under rugs or furniture. Store flammable materials away from electrical equipment. Flammable materials can ignite if exposed to sparks or heat from electrical equipment. Keep electrical panels and equipment enclosures clean and free of obstructions. This helps to ensure that the equipment can be properly ventilated and that personnel can access it safely. Report any electrical hazards to the appropriate authorities. Do not attempt to repair electrical hazards yourself unless you are a qualified electrician. Be aware of the location of underground utilities before digging. Contact the local utility companies to locate underground utilities before digging to avoid damaging them. Follow lockout tagout procedures when working on electrical equipment. Lockout-tagout procedures ensure that the equipment is de-energized and cannot be accidentally energized while work is being performed. Use caution when working near overhead power lines. Maintain a safe distance from overhead power lines to avoid electric shock. Be aware of the symptoms of electric shock. The symptoms of electric shock can range from mild tingling to cardiac arrest. Seek medical attention immediately if you suspect that you have been exposed to electric shock. Know how to respond to an electrical emergency. This includes knowing how to shut off the power, call for help, and provide first aid. By following these safety tips, you can help to prevent electrical accidents and injuries. Electrical safety is everyone's responsibility. It is also essential to understand the impact of different types of motors on the overall system design and protection. For instance, energy-efficient motors, while beneficial for reducing energy consumption, may have different starting current characteristics compared to standard efficiency motors. This difference in starting current can affect the selection of overcurrent protection devices. Similarly, the use of synchronous motors, which have a different operating principle than induction motors, may require specialized protection schemes. Furthermore, the type of load connected to the motor can also influence the selection of branch circuit protection. For example, motors driving centrifugal pumps or fans may experience different load profiles than motors driving reciprocating compressors or conveyors. The load profile can affect the motor's current draw and the potential for overloads. Therefore, it's crucial to consider the specific application and load characteristics when sizing branch circuit protection. In addition to the NEC requirements and manufacturer recommendations, it's also important to consider industry best practices and standards. Organizations such as the Institute of Electrical and Electronics Engineers, or IEE, and the National Fire Protection Association, or NFPA, publish standards and guidelines that provide valuable information on electrical safety and system design. These standards can help to ensure that electrical installations are safe, reliable, and compliant with industry best practices. Finally, it is important to emphasize the importance of ongoing training and education for electrical personnel. Electrical technology is constantly evolving, and it's crucial for electrical personnel to stay up to date on the latest codes, standards, and best practices. Regular training can help to improve their knowledge, skills, and safety awareness, reducing the risk of electrical accidents and injuries. A comprehensive understanding of motor protection principles, ASD characteristics, and applicable codes and standards is essential for ensuring the safe and reliable operation of electrical systems. By following the guidelines outlined in this narration and consulting with qualified professionals, you can make informed decisions about branch circuit protection and other electrical safety measures.